Okay, so today I'm going to explain you the important topic in statistical mechanics, that is the relationship between entropy and thermodynamic probability. That is the relationship between entropy and thermodynamic probability. So we know that a system, when the system is at equilibrium, it has highest entropy. Similarly, when the system at equilibrium, it has highest or maximum thermodynamic probability. So entropy is in some way proportional to thermodynamic probability, or entropy is a function of thermodynamic probability. So this equation I am going to explain you and derive this equation step by step to explain you the important property in statistical mechanics, that is the statistical entropy, or in other words the relationship of entropy with thermodynamic probability. We know from classical thermodynamics that the system has the highest entropy or maximum entropy when the system attain equilibrium. Similarly, a system has maximum thermodynamic probability when it is at equilibrium. So it has maximum thermodynamic probability. So we can write down in terms of proportionality that entropy in some way proportional to thermodynamic probability, or entropy is a function of probability. Consider two separate systems A and B, which consist of particle in some way, in somehow order way, system A and system B. After mixing, the particle are distributed randomly, and this system is represented with AB. Now we are representing the two property of system A and system B. So the entropy of the system A is represented as A, and thermodynamic probability is WA. In term of in the form of equation A, the entropy of system SA is a function of WA. Similarly, for the system B, the entropy with the is B, and probability with WB, or is B is a function of WB. After mixing, the entropy of system AB is represented as AB. Similarly, of thermodynamic probability of system AB is represented with WAB. We know that entropy is an extensive property, that is an additive property. The total entropy is the sum of individual entropy, that is SAB is equal to SA plus SB. And thermodynamic probability, we know that for the two system or for the two level, this is the product of different individual system. So WAB is equal to WA times WB. Now we can write down this equation taking here and putting the value of SAB, SA plus SB. So SAB is a function of WA into WB in the same way here, and this SA is a function of WA plus FW. So we got equation X. This equation X is very important equation. From this we can derive our desired equation. Now in the first case, we have to differentiate this equation with respect to WB, keeping WA constant. So we differentiate with respect to WB, keeping WA constant. So this term is a constant term, so differentiating this term, we will get a 0 for this, and the other term already consists of the same term, so we will get the term will be here. Now just applying chain rule to this term, left hand side term, we can apply chain rule. So this d f is a function of xy, so we can express this, expand this in this form, because this term can be cancelled with each other and we have the same term here right now here. So applying to this equation y the chain rule, so we have this term, left hand side term, and after applying chain rule we got in the same way, we got WA into WB and dWA into WB, and this is the same term we expanded here. Just putting this value in that equation y, the right hand side is the same one, and we applied chain rule to the left hand side. In this left hand side, this is the same term, but this can be cancelled some term because this WA is constant, so we can take out from the British sign, and DWB will be cancelled with each other, so we got WA only here. This is the same term and this is also the same term, can't be cancelled. Now we can apply this equation, we can multiply this equation, both sides of this equation with WB. So we got this equation 1, WB is multiplied here and also here. In the same way, if we differentiate equation x with respect to WA and keeping WB constant, so this is vice versa, so we will get the same equation. You can look here, so you can get the same equation almost, but the right hand side is different because we differentiate in this case with respect to WA, and in this case we already differentiated with respect to WB and keeping WB constant here. So if we compare equation 1 with equation 2, so the left hand side are equal, so comparing the left hand side of both the equation, we got this equation 3. If you look this equation 3, we have this for individual system, this is for the system B mostly term, and system A is kept constant. In this case system B is kept constant, and this is for the system A. Equation 3 can be written in the form in which both the right hand side and left hand side we can make equal to a constant term, that is k. So this term we can make equal to a constant, and this term also we can make equal to a constant. Or generalizing this equation, it's very important because this is for individual, we just eliminate this term, so we can get a very general equation because this is easy to solve, this general equation. After rearranging this equation, so this term can be transferred to another side, so we got this term, and this term can be solved in mathematics. If we have for example, if we have this is some kind of if you take differential of log ln x with respect to x, so we are getting 1 over x, or transferring this dx to another side, so we have 1 over x dx d ln x. So we got the same form here. This is a kind of differential equation which can be solved by integrating this equation using indefinite integration, that is without limits. So this differential can be solved. This d f w, because we know that s is a function of w, so just replacing this f w with s, this term only, so we have ds is equal to k d ln w. Now integrating, after integration, this differential will be cancelled with integration, and this differential similarly will cancel integration, but we have constant of integration, and this constant of integration is the entropy at absolute zero, that is temperature is minus 273.6 Kelvin. From the third law of thermodynamics, that the entropy at absolute zero is 0. In this equation where k is Boltzmann constant, Now I'm giving you a question that is find the thermodynamic probability or statistical entropy for a system which consists of two distinguishable particles distributed in energy states 3 gi is equal to 3. So this is just I give you hints, that is we have three energy states and these are two distinguishable particles. So just find statistical entropy for this system.